Today we'll be discussing the types of reactions that we can see in chemistry. So the first thing that we're going to do is we're going to get out some Post-its, and we're going to create a mini flipbook inside of our notebook so that we have both just kind of a general overview and then more detail on the inside. So as I go through these, I will be flipping up the Post-its. If you need to take a second, pause the video to write down everything that is underneath the Post-it, that is totally fine. But we're first going to talk about the type of reaction, first of which is going to be synthesis. Now synthesis, you most likely have heard this word before. Perhaps it is bringing to mind the word photosynthesis from your days in biology, and synthesis means to create something. So with synthesis, we are going to take two things and form them into one thing. So here we have a example with a relationship. So we have a male and a female coming together to form one single couple. And as a nickname for this type of reaction, I like to call it the hookup, because we are bringing things together and forcing them to become one. So again, these reactions are going to be putting things together. I'm going to have two or more reactants, and they're going to produce a single product. I have my general statement here of A plus B goes to AB, and then I have a real-world example, which is going to be that two molecules of diatomic hydrogen gas plus one molecule of diatomic oxygen will come together to form two molecules of dihydrogen monoxide, or water. And this is a very simple synthesis reaction. Again, I have two products coming together to form two reactants coming together to form one single product. Next, I have the opposite of synthesis, and that is going to be decomposition. Now, decomposition, as we can see here from our general relationship analogy, we have a couple and they are breaking up. They are going from being together to being apart. And so my analogy for the decomposition reaction is going to be the breakup. So whereas synthesis put things together, my decomposition reactions will be taking them apart. My single reactant will break down into two or more products. I have my super general example of AB goes to A plus B. And I have my real world example, which is going to be calcium bromide decomposing into calcium and diatomic bromine. So now that we have those types of reactions all set for us, we're going to go ahead and we're going to keep moving on. Now I have two more here that are going to look a little bit different from the ones previously, as they are new types. So my very first one is going to be the single replacement reaction. The single replacement reaction, I am going to have a couple plus a single person going to a couple plus a single person. And I like to call this relationship the homewrecker. Whatever new thing I have introduced is going to break up the pre-existing compound and replace one of those compound's components. So as we can see here, my female figurine there in the black skirt was replaced with my green girl in my final product. And so for my single replacement, I'm going to have a single element is going to replace a second element in a compound. So I have our super general formula of AB plus C goes to AC plus B. And for my actual real life example, I have two potassium iodide molecules plus one diatomic bromine going to two potassium bromide molecules plus one diatomic iodine. So as you can see here, my bromine has kicked out iodine. It was the homewrecker. It broke up that potassium and iodine couple and replaced it. My next type is going to be that of the double replacement, and I refer to this as wife swap or swingers. With Wife Swap, it was an old TV show, not sure if you ever seen it, but if you had, they end up switching wives and learning from each other. There's a reason that you might not have seen the show. But anyway, so I have two happy couples, and when they see each other, they realize they're not actually very happy with their partners, and they would much rather exchange partners and be with someone that they like better. So I have this, my black skirt and black shirt male and female couple introduced to a blue and a green couple, and they are going to break each other up, but stay together with their previous partner's person. I don't know. That was a bad explanation. My apologies. Anyway, here we go. So we have two compounds that are going to be exchanging components. So I have AB plus CD is going to go to AD plus CB. And so as you can see, A was with B, but now A is with D, and C was with D, but now C is with B. So I have exchanged my partner. And then in my real life example, I can see potassium iodide plus lead 2 nitrate going to potassium nitrate and lead 2 iodide. I have switched my partners, and therefore I am a double replacement reaction. Last type of reactions here, I have combustion, which you may have noticed does not have a stick figure diagram to go along with it. It instead has a flame. Combustion reactions are very commonly associated with fire. That's what it means to combust, is to light on fire. And my analogy for that is going to be hot mess. And you will see why combustion reactions are a hot mess on 2 levels. So my combustion reactions are going to take place when I have a hydrocarbon, hydro meaning hydrogen and carbon meaning carbon. So I have a carbon-hydrogen molecule being added to oxygen, and that reaction producing carbon dioxide and water. Now you'll notice the only piece in my description that was not an explicit element already, or an explicit compound, was the hydrocarbon. I have C sub X and H sub Y. That is because I can have a multitude of different options for how many carbons and how many hydrogens are going to be in that hydrocarbon. It does not matter that much. What is going to stay the same all the time, though, is that I will always be adding it with oxygen, and I will always produce carbon dioxide and water. These three stay the same all the time. This is the only thing that can change, and it's just going to be the subscripts that are going to change, not the actual like completely different elements, such like that. And the reason that I like to call this a hot mess of a reaction is that I have a couple plus a single person, so it looks like a single replacement at first, but then when we move to the products, we notice, oh wait, oxygen did break up that couple of carbon and hydrogen, but instead of only getting with one of them, oxygen got with both of them, and so oxygen is a hot mess, and so we like to call this the hot mess reaction. My very last type of reaction is going to be redox, and for my redox reaction, I have a little phrase that you can use to help yourself, and that is going to be Leo the lion goes grr. Okay, so imagine a little lion, you've named him Leo, and he's growling at you, okay? And Leo is going to stand for loss of electron oxidation, okay? So L-E-O, Leo, and then GER, spelled very strangely, G-E-R, is going to be gain of electrons reduction, G-E-R, okay? So with my redox reaction, it's not truly its own type of reaction. Instead, it's more of a more in-depth description of the events of what happened to each element inside of the reaction. And so to reduce is going to be having my oxidative state become a lower number. Now what's important here is to remember that negatives are lower than positives. So even if I am gaining electrons, my oxidative state, my charge, is lower because I will have a negative number, and so I can reduce even if I am gaining electrons. Whereas to oxidate is going to be the opposite, is going to have a oxidative state becoming higher. Remember that this, again, positive numbers are bigger than negative numbers, and 0 is bigger than any negative number, okay? So my oxidative state, if it gets higher at all, I have oxidated. Couple of things to note here. I have that my oxidative state for a single atom not bonded to anything is going to be 0. This is because I do not have a charge, and what oxidative states are is a fancy way to say charge. So since I do not have a charge, I will have a charge of 0. My oxidative state will be 0 if I am by myself. Now here we have a reaction. We have iron, which is bonded to chlorine, plus a diatomic oxygen, going to iron bonded with oxygen and a diatomic chlorine. Now, iron did not change its environment at all. It has a positive 2 charge on both the reactants and the product side, and so iron was not oxidized nor reduced. But I can see that my oxygen, which went from being alone to being within a compound, that is going to be a reduced oxygen. And so oxygen will have gone from 0 in its diatomic state to -2 when it formed a compound, because it will have stolen 2 electrons. And negatives are less than 0, or a positive number, so my oxygen was reduced. Where my chlorine, on the other hand, went from being inside of a compound to being by itself. So it went from having its normal compound charge of -1 to suddenly having a charge of 0, since it was by itself as a diatomic molecule. And so my chlorine was oxidized and my oxygen was reduced.